This work has been done in collaboration with a PhD student who is Guillem Rosselló, who is finishing his thesis work now. And then with Rafael Sanchez, that is now, well, before he was in the University of Carlos III of Madrid, and now he's in a different university in Madrid. And well, this work indeed was, we started this work very long time, but at the end we managed to finish. So the outline of the talk is the following. First of all, I would like to motivate why we want to study this problem. Then our treatment is restricted to the linear response regime. Then I will describe briefly the theoretical model that we use. And then we are going to focus on the case where we have a system that is a quantum dot and is coupled to an electromagnetic environment. And from there, we are going to study thermoelectricity in the way that we are interested on the Seebeck asymmetry and also on what we call thermal asymmetry. Also, we are going to analyze how is the heat rectification in this system. And we have to remember that we are in the linear response regime. So heat rectification is quite unusual in the linear response regime. Then we are going to use this device as a heat engine. And then we are going to define the efficiency and the power. And then at the end, I'm going to summarize all the conclusions extracted from this work, and then I will give you some outlook about what we can do. Here, the main topic of the workshop is quantum thermodynamics, and then one of the aspects that is interesting in this field is that with the emergence of many different devices now that, for instance, consider topological effect or nano devices, then since all of these setups are integrated in circuits for practical applications, then it's important to know how these systems dissipate, how the heat is distributed along across these devices, and how we can manipulate the heat and the charge current in these systems. So then we know that in nanostructures like this one, that is a quantum dot, we can apply some forces like electrical forces or thermal forces. These are indicated here. So this B and theta are electrical voltage and thermal gradients. They drive some charge current, or similarly, they are also able to drive a heat current. So then here I just write down the linear and the nonlinear, the leading order in the nonlinear expansion for the current, the charge and the heat current. But for this work, we are going to concentrate only in the linear response. So in the first coefficients, this is the linear conductance, the electrostatic linear conductance, and this is the electrothermal linear conductance. So we are going to neglect the nonlinear terms. And the same for the heat current. So then, since we are interested in these currents, we are going to specify that indeed our focus is on the way in which in these conductances that we have seen before, there is no way, okay. These conductances that we have seen before, here this GL M or K, then there are some relations between them. So what we want is just to focus on the case in which these relations for these relations are broken. Okay. And these relations are broken in our case because of the presence of inelasticity. Okay, so we can just write down the linear response transport for the system in a very schematic way with this matrix that is the Onsager matrix. And then, as I said before, there are some relation between these elements. For instance, we have from micro-reversibility that the Onsager matrix is a symmetric matrix when we invert the magnetic field, for instance, if we consider a magnetic field in the system. And then this allows us to have a relation between L and M. This is the electrothermal, and this is the thermoelectric conductance, and this is the electrothermal conductance. Okay, so there are extra symmetries that are imposed by the fact that the S matrix that describes the transport in our problem is unitary. So then from there we can derive these relationships. So now we are interested on this relation, this middle relation, because this is some people before have pointed out that this relation is broken in the presence of inelasticity. So this is indeed the several works in which the presence of inelasticity breaks down this symmetry that we are going to call the Seebeck symmetry. Okay. So in our case, the inelasticity comes from the fact that we have an electromagnetic environment. So we study a quantum dot that we know, all of you know that is a confined system with discrete levels in which if you put some electrons in this zero-dimensional system, then there is some Coulomb repulsion between the electrons. And the nice thing of this object is that you can couple reservoirs and then you can make transport. So, okay. So then in quantum dots, all of you know that you can observe the Coulomb blockade phenomenon, in which if you want to make some transport through an island like this, to barriers, to contact the dot energy level, then if there is an electron here, then it's possible to transport another electron from left to right if this chemical potential is above this energy level, that is the one that you get when you have two electrons there and you feel the Coulomb repulsion. In the case in which this Coulomb repulsion is large enough, then transport is blockade, for instance, right? Because you don't have enough energy to overcome the Coulomb repulsion on the dot. So this is, in a very easy way, this is described with this model in which you consider the discretized version of the Poisson equation, like this equation here with a geometrical capacitance C. And by having this equation in which this potential here is the internal potential of the dot, you can obtain the energy potential for this system, and then from there you can describe properly the Coulomb blockade effects. Okay, so in our system we consider that we have Coulomb repulsion modeling with the previous equations, and also we consider that our quantum dot is coupled to the electromagnetic environment. Then this is translated in the way that now the electromagnetic environment is encapsulated in an impedance. So our quantum dot is somehow coupled to this environmental impedance. And this is indeed described by a function that is called usually the P of E function. This function indeed takes into account that due to the coupling with the environment, the voltage or the charge in the dot fluctuates. So this function takes into account that the voltage fluctuations, the voltage correlator. So this is a very well-known theory for transport with electromagnetic environment that is described mainly in this reference. So then, in the simplest case, we have a tunnel junction like this with a barrier and two contacts described this way with the two reservoirs and the coupling between them. And here there is some phase that takes into account that the voltage can fluctuate anytime that the tunnels take place. So considering this model and these voltage fluctuations because of the environment, then one is able to calculate the current. And what is very nice here is that in the case that we use this Fermi-Golden rule, then we can prove easily that the transition rates for calculating this current, they contain the effect of the voltage fluctuations. So then these transition rates are just an integral that consider the electron and hole excitations, but these are weighted for with the fact that the voltage is fluctuating because the system is coupled to some external environment, some electromagnetic environment. So this is the root of this transport description. At the end, this P of E function is given by this expression where this J is indeed something that looks complicated. It depends on this impedance that I said before, and this impedance takes into account the fact that the voltage is fluctuating. So in our case, we just focus on the case in which the environment is resistive. So the impedance is just a resistance. And then if we consider this situation and we calculate explicitly this P of E function, then we end up with a Gaussian function. So somehow the fact that our dot level is coupled to the environment is translated in the situation in which this level is indeed somehow broadened by this function that is a Gaussian. Okay. So this is our situation. We have two capacitance, our dot here, and it's coupled to this impedance here. Okay. Okay, so yes, this is our device. We consider that we have two different capacitance, CL and CR. This is again translated in the fact that now the left and right sides, they see different environments because they are coupled to different P of E functions. In this work, we have considered two situations. First, the case where the dot is occupied just by one electron, 0 or 1, or the spinful case, where we have four states. We can have the empty state, the state in which the dot is singly occupied with up or down electrons, or the double occupied state. In the case in which the dot can be occupied by two electrons, this is the spinful case, then the electrochemical potential of the dot, how the dot level is renormalized because of the interactions, depends on the charge state, and then we consider that we can have 0 or 1 when this chemical potential S is equal to 1. This means that the dot is doubly occupied.
Okay, so but this is for the last part of the system. Mainly we consider that the dot is just coupled to the dot is just occupied by 0 or 1 electron. It's coupled to this environment, differently for left and right side. And then we consider this parameter that is important for us, that is the asymmetry between the capacitance. Okay. So our description is quite simple. It's just master equation. Here is the full case where we can have 4 states. And these gammas, they are the transition rates in our system. Okay, so the currents, we are interested in calculating the currents, the charge and the heat currents, are given by these transition rates with these P's that are just the occupation probabilities that we solve for the stationary case. So we put here 0, 0, 0, and then we calculate the occupation probabilities for a given rates, and then we are able to show how currents behave. Since we are considering an electromagnetic environment, we have 2 different situations. In the case that there is no environment, then the dot level is simply a delta function, because we are not considering that there is any broadening in our model description. So the rates for the chart transitions are given by this expression, and the rates for the transition in the heat current, you see that here there is some energy factor inside of this integral that considers transitions in which the energy is transported. So in these cases, we have just a delta function just located at the dot chemical potential. So in our case, we have environment. So then we have to weight these transition rates, these integrals, with the P of P functions, okay? For the charge transition rate and for the heat transition rate. Okay. So first, we calculate, for instance, the electrical current in the left barrier. So the expression is quite simple because we are considering just 2 charge states. And then, since we are interested in the linear response regime, what we are going to do is just an expansion in the temperature gradient and the electrostatic potential difference. So this can be done analytically, and then we just expand the transition rates. Here we have just put some examples with very complicated integrals that depends on the environment. So by doing this, then we can calculate what I mentioned at the beginning, that is this Seebeck asymmetry. That is the difference between the thermoelectrical coefficient, conductance, for LR and RL. And the difference between them, just give me how the usual relation between them is broken. Okay. So usually, if there is no inelasticity, this is equal to this. But since we are putting some electromagnetic environment, then we are able to prove even analytically that this is not the case. The expression is quite large, but what is important is that at the end, this delta L, this is the Seebeck asymmetry, depends on this function here. And this function here depends on how the P function for the different contacts, L and L prime, overlaps. So this can give us some intuition about how this Seebeck asymmetry behaves when we study such asymmetry
as a function, for instance, of the capacitance asymmetry. So first, we see just from the analytical result that this x function here is non-zero only if there is an asymmetry in the capacitance, in the CL and CR. And also that this depends strongly on the overlap of the p function of different sites. Okay, but it's also important to mention that this asymmetry does not depend on the differences between the tunneling rates of the two variables. Okay. Okay. So these are mainly the results. The Seebeck asymmetry is plotted here as a function of this capacitance asymmetry. And we see that if this asymmetry is zero, then this Seebeck asymmetry is null. Also, it changes sign with this asymmetry. And if we make a cut here for a given kappa value or asymmetry for the capacitance, we see that it changes sign with the dot level position. And we also see that as long as the sum of the two capacitance, CL and CR, the sum of the two is given by this C, increase, then the asymmetry for the Seebeck increase. Why is this? Because if you increase this C, then since the two P of E functions are Gaussian, then they are indeed centered on the charging energy that is depends inversely on this C, then you have narrower Gaussian distributions and the overlap between them is maximum. So by increasing C, the sum of the two capacitance, you can increase the Seebeck asymmetry. Okay, we also have studied the heat rectification, and the heat rectification is defined in this way. So we calculate the heat at the left side, at the right side, but we invert the gradient, the thermal gradient in the two cases. And in that case, we can see that in the linear regime, this heat rectification is composed by these two terms. This one is zero because of the Onsager symmetry, and then there is only this term here that tells us how the heat is rectified in the linear response region in our system. Okay, we can also define this coefficient that is normalized, but at the end, everything depends on this KLL and KRR difference. Okay, so in this case, it's important to see that now this heat rectification is composed by two terms. Okay, if we again make some analytics, then we can separate two contributions, this one and this one. So the heat is rectified when there is some asymmetry between the capacitance, this is this term, but also when there is some asymmetry between the gamma L and gamma R. These are the tunneling rates or the tunneling amplitudes different for each barrier. So one asymmetry has a kinetic origin and the other one has an electrostatic origin. And again, the electrostatic origin of this heat rectification depends on this x function that depends again on the overlap of these functions, of the P of E functions. And I'm going to just finishing this more or less. Here we can see that again this heat rectification when we tune the capacitance asymmetry is stronger as long as C is stronger, and so just the opposite. as long as this C is smaller. And what is important is that here, if we tune C, then we can control somehow the heat rectification in the system. And well, also we can see how the system rectifies the heat or the thermal asymmetry when we tune the barrier asymmetry, and we see that it's almost independent on C. It only depends on this lambda, and it changes sign when we change lambda. This happens, so we have this symmetry because electrons spend different times in each barrier because you have these gammas that are different for left and right barriers. So they are feeling in one of the barriers more the environment than in the other one. For this reason, you have some heat rectification in the linear response regime, and the origin is kinetic. And well, I think that I don't have more time. Just to mention that the system also can work like an engine. We can, by applying a thermal gradient, we can drive some current against the applied voltage, and then we can define some power, and this power. I mean, we can define this power and this efficiency, and we can maximize the power at this voltage and define this efficiency at the maximum power. These are the analytic expressions for the maximum power, and this is the Carnot efficiency in our system that consider the fact that we have the environment. And what we can see here is that we are able to get a maximum efficiency that is not that is quite big at not very low power. I mean, our efficiency can be high enough, and this is also achieved when the power is not so low. Normally, you get the maximum efficiency when the power is negligible. But in our case, we are able to prove that we can achieve reasonable efficiencies for not very low power. And well, we have also investigated the same for double occupancy, and the characteristics are more or less the same. And the conclusions are just this. We have investigated the inelastic effect in this thermoelectric device. We can explicitly demonstrate that the environment effect can promote heat transport. We have also studied the symmetry relations that are violated because of the inelasticity, and also because we have some internal asymmetry, for instance, due to the electrostatic asymmetry between the two capacitance. And also we have demonstrated that we have that the environment can cause heat rectification in the linear response regime, and also that asymmetric couplings can improve efficiency. And finally, well, the outlook, I don't know, doesn't work very well, and I think that I can stop here because, okay. Outlook is, well, we can consider different types of environment. Here we have considered a high impedance environment, but we could also consider a low impedance environment. And well, we can do many things. So, and thanks for your attention and time for questions.